Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5 and today we are going to present about stationary and partial differentiation. This is our group members. First, Nur Izzah binti Mohd Ramli. Second, Nur Fatihah binti Mohamad. Third, Aini Hafizah binti Junaidi. Fourth, Nur Zahirah binti Mohamad. And lastly, Ahamed Zahrani bin Syed Badhrudhja. First, stationary points. Stationary points occur when we have dy over dx equal to 0. This represents when the gradient of a curve is horizontal. We have three types of stationary points, which is local minimum, point of inflection, and local maximum. First, local minimum. We can see that when we have a point that passes through a minimum, the gradient goes from the negative, which is f prime x less than 0, or dy over dx less than 0, to positive, which is f prime x more than 0 or dy over dx more than 0. Second, point of inflection. We can see when we have a point that passes through the point of inflection, we should note that the gradient remains of the same sign, which is either positive both sides or negative both sides. Third, local maximum. When we have a point that passes through a maximum, the gradient goes from being positive, which is f prime x more than 0 or dy over dx more than 0, to being negative, which is f prime x less than 0 or dy over dx less than 0.
Okay, let us continue to the classifying stationary point. Okay, now we need to introduce the second derivative denoted d square y over dx square, or we can call it as f double prime x. This means that we differentiate the function twice. So for example, if we have y equal to 2x cubed, we will first find dy over dx, which is equal to 6x squared, which we will then differentiate again to find d square y over dx square, which is 18x. Okay, the second derivative is used to decide whether a stationary point is a maximum or a minimum. If we have the value of x of a stationary point, then we substitute this value into the second derivative. If d square y over dx square is more than 0, so we will get a positive value. Then we have a minimum stationary point. If we have a d square y over dx square less than 0, so we will get a negative value. Then we will get a maximum stationary point. Unfortunately, this test fails if we find that d square y over dx square is equal to 0. In this case, we could have a maximum, minimum, or point of inflection, and then we must carry out the following further test, which is second test, in order to decide. Okay, for the second test, first find two x values just to the left and right of the stationary point, and calculate f prime x for each. If f prime x left is more than 0 and f prime x right is less than 0, so we have a maximum stationary point. If f prime x left is less than 0 and f prime x right is more than 0, so we have a minimum stationary point. And lastly, if f prime x left and f prime x right have the same sign, which is either both are positive or negative sign, then we have a point of inflection.
Okay, we continue with the question that related to stationary points. Okay, first question, we need to find and classify the stationary points of y is equal to x power of 4 over 4 minus with x power of 2 over 2. So first we need to find when dy per dx is equal to 0. We need to find where the stationary points are. So dy over dx is equal to x power of 3 negative s is equal to 0. So, and then x in bracket x power of 2 minus with 1 is equal to 0. And then we need to separate them by another equation that x minus with 1 and multiple with in bracket x plus 1 is equal to 0. Therefore, we have stationary points at x is equal to 0, x equal to 1, and x equal to negative 1. So we need to classify them first by finding the second derivative. Okay, now we have d2y over dx2 is equal to 3x power of 2 negative 1. So we need to substitute our x value for the location of the stationary points into d2y over dx2. Okay, now when we have x is equal to 0, we have d2y over dx2 is equal to negative 1. So our d2y over dx2 is less than 0. It means that it's a negative. So this is a maximum. And when s equal to 1, we have d2y over dx2 is equal to 2. Hence, our d2y and over dx2 is more than positive. It's more than 0, so it's positive. So this is a minimum. And lastly, when x is equal to negative 1, so we again have d2y over dx2 is equal to 2. So our d2y over dx2 is more than positive. So this is the positive. So this is a minimum. Okay, we continue with the next question. Okay, look at the first equation. Y is equal to x power of 3. Okay, first we need to find when dy over dx is equal to 0, we have stationary points is x is 3x power of 2 is equal to 0. So our x is 0. So we have stationary point at x equal to 0. We need to classify this point by finding the second derivative first. Okay, our d2y over dx2 is equal to 6x. Okay, now when x is equal to 0, we have d2y over dx is equal to 0. And hence our test failed and we must carry out further tests. So we need to pick x value close to the other side of the stationary points at x equal to 0. So x value just to the left would be x left is equal to negative 0.5. And one just to the right would be xr is equal to 0.5. So now as dy over dx is equal to fs minus v is equal to 3x power of 2. Now we have fsl is equal to 3x left power of 2 is equal to 3 multiple with negative 0.5 power of 2 is equal to 0.75 is more than 0. And then fsr just to the right is equal to 3xr power of 2 and then equal to 3 we need to multiply with 0.5 power of 2 is equal to 0.75 is more than 0. So both fs left is more than 0 and fsr is also more than 0. So they are positive and the same signs. So our stationary points at s is equal to 0 is a point of inflection.
Let's continue with chemistry example. The question is, the Lennard-Jones potential describe the potential energy V between two helium atoms separated by a distance r. The equation and graph of this function are shown below. Vr equal to A over r to the power of 12 minus B over r to the power of 6, where A and B are constant. The two particles are at their equilibrium separation when the potential is at a minimum, which is V is at a minimum. By differentiate this equation with respect to r, find the equilibrium separation. To find the minimum V, we need to differentiate it and then set it equal to 0. dV over dr equal to 0. Then, the value of r will be where the potential is at my minimum. Differentiate v with respect to r will give dv over dr equal to negative 12a over r to the power of 13 plus 6b over r to the power of 7. We need to find where dv over dr equal to 0, so we need to solve this equation. Negative 12a over r to the power of 13 plus 6b over r to the power of 7 equal to 0. And then we need to add negative 12a over r to the power of negative 13 to both sides. 6b over r to the power of 7 equal to 12a over r to the power of 13. Then we multiply each side by r to the power of 13 and divide by 6b. So we will get r to the power of 13 over r to the power of 7 equal to 12a over 6b. And then we simplify both of the fraction. So we will get r to the power of 6 equal to 2a over b. And then we take the square root of both sides. So we will get r equal to 2a over b. All of them will be to the power of 1 over 6.
Next, partial differentiation. Partial differentiation is used to differentiate function with multiple variables. We do this by differentiation with respect to one variable and treating all other variables as constant. Let me see this equation. Y equal to f x in bracket z. The partial derivative of a y with respect to s is denoted as in bracket delta y equal to delta x, and while z as a constant. Partial differentiation also used in ideal gas equation as seen below. P equal to nRT over V. The pressure of a gas depends on its volume V and the temperature T it is. We often find it useful to calculate how one variable changes with one other while the remaining variables are seen to be constant. These are the example equations related to the partial differentiation to make you more understand. Question 1. Find delta f over delta x and delta f over delta y for that equation. X power of 2 minus 1 in bracket and y plus 2. So at the left side, first we find delta f over delta x. So first of all, we rearrange the equation in that formula. And then we put the y plus 2 at the front side. And then at the back side, we just differentiate x power of 2 minus 1. And it becomes 2x. So the final answer is 2x in bracket y plus 2. We don't need to differentiate y plus 2 because the equation just need delta f over delta x. Let's move on to delta f over delta y at the right side. First of all, we rearrange the equation in the formula. Then, x power of 2 minus 1, we put at the front side. And then, we differentiate y plus 2, become 1. And then, x power of 2 minus 1 times multiple 1. So the answer is, final answer, x power of 2 minus 1. Question 2. Find delta f over delta x and delta f over delta y for that equation. E power of negative x sign in bracket x plus y. So first of all, we find delta f over delta x using the product rule. First, we rearrange the equation in that formula. Delta f over delta x. And then, we rearrange E
negative e power of negative x sine in the bracket x plus y plus e power of negative x in the bracket 1 time of cos in the bracket x plus y. Sine x plus y is converted to 1 time of cos x plus y using the product rule. And then the final answer is e power of ex in the bracket cos x plus y minus sine in the bracket x plus y. Secondly, we find delta f over delta y with similarly using the product rule. First of all, we rearrange the equation in that formula, delta f over delta y. Then, differentiate delta e power of negative x sine x plus y, it becomes 0. And then plus e power of ex in the bracket 1 time of cos x plus y. And then the final answer is e power of ex cos in the bracket x plus y.
The application question of partial differentiation is number 1. The ideal case equation is PV equals to nRT. Find delta V over delta T. Answer. Firstly, rearrange the equation. V equals to nRT over P. Then, delta V over delta T equals to delta nRT over P over delta T. Therefore, delta T over delta T equals to nR over P. Second question is, the ideal gas equation is PV equals to nRT. Find delta T over delta P. Answer. Firstly, rearrange the equation. T equals to PV over nR. Then, delta T over delta P equals to delta PV over nR over delta P. Therefore, delta T over delta P equals to V over nR.